Good morning, friends. In last lecture, we discussed about amplitude, phase constant, and also what is the periodic time and frequency and angular frequency, and we obtain the equation of this. And we also do the graph of the amplitude versus time. Also, we discuss about the relation between the angular frequency and periodic time t. We obtain the t is equal to 2 pi upon omega, and also omega is equal to 2 pi f. Okay. Now today we are going to discuss about what is the velocity and acceleration of a simple harmonic oscillator, or in other words, the particle performing a simple harmonic motion. Generally, for simple harmonic motion, we consider the motion of a pendulum of a wall clock. Right? Like to this manner. One pendulum is oscillate. This position is its equilibrium position, x is equal to 0. Now, it performs the simple harmonic motion about this to extreme point. X is equal to plus a, x is equal to minus a. So, out of this path, at which point the velocity of a simple harmonic oscillator is maximum, and at which point the velocity is minimum. That means the 0. So we know that during the motion, pendulum will oscillate like this way. First it goes to the extreme point here. For one moment it remains stationary, therefore its velocity is 0. And then it starts its motion in opposite direction. Therefore, the direction of motion is seen at this point. Because during the simple harmonic motion, the force acting on a particle is towards the mean position and directly proportional to the displacement of a particle at that instant of time. So as the distance increases, so force acting on a particle is going to increase. That is the restoring force. And due to that reason, after traveling some distance, so the particle for one moment remains stationary, and then it starts return back. Again goes to this direction. After the mean position, the force starting to act on this particle in opposite direction. Therefore, at this point, for one moment, the particle remains stationary. Thus, at extreme point, its velocity is 0, and at mean position, its velocity is maximum. We want to prove this thing, and also what's the equation of the velocity, instantaneous velocity at any instant of time t. And also we discuss its special cases. Okay. How we obtain the velocity? Because for simple harmonic motion, we know the displacement of a particle performing the simple harmonic motion is xt is equal to a cos omega t plus phi. Here is the amplitude, omega is the angular frequency, and phi is the initial phase. So already in chapter 3 and 4 we discussed about how we obtain the instantaneous velocity from the displacement. So differentiation of displacement with respect to time, that is the instantaneous velocity. So Vt is equal to dxt upon t. Here is, and how we obtain the instantaneous acceleration. So instantaneous acceleration is obtained at is equal to differentiation of velocity with respect to time, dvt by dt. Or in other words, let us substitute the value of vt. So that is the d by dt of dxt upon dt. That means the double differentiation of position or the displacement with respect to time, that gives acceleration. That gives the acceleration. Already this concept we learned in chapter 3. We are using this concept, we are going to obtain the equation of the velocity and also the acceleration, and we discuss its special cases. Clear this thing? Okay. Now, our question is that obtain equation of instantaneous velocity of a particle performing simple harmonic motion and discuss its cases. Discuss its special cases. For that purpose, we first assess the equation of displacement of a simple harmonic oscillator at time t. So we start from this, the displacement of a particle performing simple harmonic motion at time t with amplitude A, angular frequency omega and time t, and initial phase phi is, that is the xt is equal to a cos omega t plus phi. That is our first equation that represents the displacement of a simple harmonic oscillator at any instant of time t. Here the simple harmonic motion with amplitude A, angular frequency phi, and initial phase phi. Okay. Now differentiating with respect to time, the instantaneous velocity is Vt is equal to d by dt of x at time t. Substitute the equation of xt from equation 1, therefore d by dt, here value of xt, that is the a cos omega t plus phi. A is constant, amplitude is constant, does not change with time, therefore that is taken out. Therefore velocity, instantaneous velocity at time t is equal to a command d by dt of cos omega t plus phi. Now derivative of cos is minus sign. Therefore here minus sign function is omega t plus phi. Now derivative of this bracket, here we are taking the derivative with respect to time. Therefore the derivation of this bracket only, we have to take the derivative of the term which has the time. So only the first term, the t is present, therefore derivative of this is omega. So it's equal to minus a omega sine omega t plus phi. Omega t plus phi. So that is our instantaneous velocity at this time. Equation 2. Here we are using this concept d by dt or d by d theta of cos theta is equal to minus sin theta. Why here we take the derivative of this bracket? Because here the function cosine is the function of omega t plus phi. We are taking the derivative with respect to time. Now for our knowledge, d by d theta into cos theta is equal to derivative of cos theta is minus sin theta. And derivative of this function, that is the d theta upon d theta. So there is the 1, and due to that result, that is not written here. Here is, but in our case here, d by dt, here cosine is the function of omega t plus phi. Therefore, derivative is like that sin theta into derivative of this term omega t plus phi with respect to time. So minus sin theta as it is. Now derivative of first term omega is common, dt upon dt, that is the 1 plus phi is the constant. Derivative of constant is always 0. Here phi is the initial phase. Initial phase is constant, therefore 0. Therefore, minus omega sine omega t plus phi. Sine omega t plus phi. Just wait. So that is the derivative of our cos omega t plus phi. We directly written here. Clear it? Okay. So that is the equation of the instantaneous velocity minus a omega sine omega t plus phi. But we know that from trigonometric equation sin square theta plus cos square theta is equal to 1. Right? Therefore, sin square theta is equal to 1 minus cos square theta. Therefore, sin theta is equal to, we know that, but sin theta, here instead of the theta, omega t plus phi is equal to plus or minus under root of 1 minus cos square theta. So here cos square omega t plus phi. We know this equation sin theta is equal to square root of 1 minus cos square theta. Here we are using this concept in this equation, substitute in equation 2. So what's happened? Instantaneous velocity is equal to minus a omega. Now, plus or minus square root of 1 minus cos square omega t plus phi. So take the in this side, therefore plus or minus omega square root of s square minus s square cos square omega t plus phi. Now, our equation 1 is x is equal to a cos omega t plus phi. Therefore, that is the square of x. So it's equal to plus or minus omega under root of s square minus x square t. That is the v. So that is the equation of instantaneous velocity of a particle performing the simple harmonic motion. Now its special cases. First, at mean position, that means the x is equal to 0. At mean position, substitute the x is equal to 0 in equation 3. Therefore, equation 3 is velocity vt is equal to plus or minus omega square root of s square minus 0. X is equal to 0. Therefore, plus or minus a omega is the maximum velocity of a particle in positive x direction. V is positive, and in negative x direction, V is negative. V is negative. Now the second case, at extreme point, x is equal to plus or minus a. X is equal to plus or minus a. Therefore, equation 3 is Vt is equal to plus or minus omega s square minus s square is equal to 0. Thus, at extreme point, velocity 0 is the minimum value of velocity. So these are the two cases at minimum point, at mean position. The velocity of a simple harmonic motion or the simple harmonic oscillator is maximum, and at the extreme point, for one moment remains stationary, therefore velocity are 0, that is the minimum value. So how we obtain the equation of the velocity? Only the derivative or the differentiation of given function of position or the displacement with respect to time. So as we take the time derivative of this displacement, we obtain the equation of the velocity. Equation of the velocity is equation 2. Now we convert in that form in terms of the displacement, because the different position of the simple harmonic motion are known, and due to that reason we convert the sign into the 1 minus cos square terms. Clear this? So that is also both equation 2 and 3 are helpful to us for the numerical and also the MCQ type question. So this question also asked for the 2 marks to obtain the instantaneous velocity and discuss its special cases. Now, after the discussion of velocity of a simple harmonic oscillator, what should be the acceleration of a particle performing the simple harmonic motion? What should be the equation of acceleration, and also at which point of its path the velocity, the acceleration are maximum or minimum? For that purpose, already we know that how we obtain the acceleration. Acceleration is the double differentiation of displacement with respect to time, or the acceleration is the differentiation of velocity with respect to time. Clear? Okay, so we starting from the displacement of a simple harmonic motion. Now the acceleration is equal to the double differentiation of displacement with respect to time, or differentiation of velocity with respect to time. So the most of part of the answer, beginning part of this question, answer of this question is same as the velocity. First we have to obtain the equation of velocity. Therefore, the displacement of a particle performing simple harmonic motion at time t with amplitude angular frequency omega and initial phase phi is, that is the xt is equal to a cos omega t plus phi. That is our equation 1 is the displacement of a simple harmonic oscillator. First we obtain the velocity, therefore differentiating with respect to time. So we obtain the instantaneous velocity Vt is equal to d by dt of xt is equal to d by dt. Instead of the xt, we can write a cos omega t plus phi. Yeah, a is the constant taken out of this derivative. Therefore, Vt is equal to a. Vt is equal to a d by dt of cos omega t plus phi. Just we discussed about the derivative of cosine with respect to time. There is the minus sign. Therefore, minus a into bracket sine omega t plus phi, and derivative of this bracket is also omega. Therefore, minus a omega sine omega t plus phi. That is the V. Clear this? But we require the equation of acceleration. Therefore, again we are taking the derivative or differentiation of this function with respect to time. Now, again, differentiating with respect to time. Therefore, acceleration at is equal to d by dt of Vt. So it's equal to d by dt. Value of Vt, there is the minus a omega sine omega t plus phi. So minus a omega taken out, derivative of sine, that is the cos omega t plus phi, and derivative of this bracket is omega. Therefore, minus a omega square cos omega t plus phi. That is the acceleration. But equation 1 is a cos omega t plus phi. But from equation 1, so at is equal to minus omega square a cos omega t plus phi. So that is our equation 1. Therefore, minus omega square xt. That is the acceleration. So that is the equation of acceleration in terms of the displacement. Equation. So first, the derivative of displacement with respect to time, we obtain the velocity, equation 2. Again, we take the derivative of this equation, we obtain the acceleration, and this equation is at is equal to minus a omega square cos omega t plus phi. Now we end this equation in such a way that from equation 1, a cos omega t plus phi is our xt. Therefore, acceleration, instantaneous acceleration at time t is minus omega square xt. Now we discuss its special cases. Therefore, special cases are. So here we substitute the value of x at mean position and also at the extreme point. Here, therefore, first case is at mean position. That means the x is equal to 0. X is equal to 0. Therefore, from equation 3, the acceleration at t is equal to 0. Acceleration at t is equal to 0 is the mean position or is the minimum value of acceleration. Minimum value of acceleration. Now the second, if we substitute the x is equal to plus or minus a at extreme point, that means the x is equal to plus or minus a. So equation becomes the AT is equal to plus or minus omega square a is the maximum acceleration. Maximum value of acceleration. In positive x direction, acceleration is negative, a is negative, and in negative x direction, a is positive. So these are the cases, first at the mean position and second at the extreme position. There is the opposite to the velocity. Velocity is maximum at mean position, but acceleration is 0. While the velocity at extreme point is 0, here the acceleration are maximum at extreme point. The similar way of velocity, we obtain the equation of the acceleration by taking the double derivative or the double differentiation of displacement with respect to time, and we obtain the instantaneous acceleration, this equation. Now just we get the equation of velocity and acceleration. Maximum velocity is plus or minus a omega, and maximum acceleration is plus or minus omega square a. Now we are going to attempt the question is that do the graph of displacement versus time, velocity versus time, and acceleration versus time for a simple harmonic oscillator. Do the graph of displacement versus time, velocity versus time, and acceleration versus time, at versus. For that purpose, the graph is this manner. There is the time t. First, here we take the displacement. That is our xt is along the y-axis. So these are the points. At time t is equal to 0, the motion is started from positive x is equal to plus a. X is equal to plus a pi. So there is our x is equal to plus a. And there is our x is equal to minus a. Now this time t by 4, next t by 4, next t by 4. Okay. Therefore, motion is started like this manner. At t by 4 time, it reaches at the x is equal to 0. Again here the maximum. Again becomes the 0 at this point. again becomes the maximum here. So there is the graph of displacement versus time for a simple harmonic oscillator performing the simple harmonic motion. Now, what should be the graph of the velocity versus time? So graph of the velocity versus time is also the same manner. Already we discussed the cases of the velocity. At mean position, the velocity is maximum, and at extreme point, the velocity is 0. So there is a x is equal to plus a minus a. Plus a minus a. Now, there is a time interval are same for the acceleration, velocity, and also the displacement. Okay, that is the x is equal to 0 position. Here the displacement is 0. Here the displacement is maximum. So our graph is like this manner. So there is the velocity versus time graph. Here the phase difference between the displacement and velocity is pi by 2. Is pi by 2. Now the graph of the time acceleration versus time. Velocity at mean position is 0. Here the acceleration is maximum. Therefore there is the plus a, there is the minus a. Acceleration is in this direction. There is the x is equal to 0. There is the plus a, there is the minus a. So at the mean position, the acceleration is negative. Therefore, graph is like this manner. And at this point, there is the maximum. Again here 0. And again here, there is the maximum. So that is the graph of acceleration versus time. Here it is. Okay. Now, some important points from this graph is that there is important for the 1 mark subjective question. The ratio of maximum acceleration to the maximum velocity is, that means the A maximum upon V maximum. We know that the equation of the A maximum is omega square A, and here plus or minus A omega. A cancel, 1 times omega cancel, therefore omega is equal to 2 pi upon T or the 2 pi F. There is the value of ratio of maximum acceleration to the maximum velocity. Now the second point is that from graph, the phase difference between displacement and velocity and velocity is pi by 2, and between displacement and acceleration is pi. While phase difference between velocity and acceleration is pi radian. Whereas, so these are the graph and also the important point from the displacement, velocity and acceleration versus time.